Hello, welcome to lesson 6. I'm Daniel. I'm here with Stephanie and Derek.
Yep.
And so I'm going to start with number 1. So 1A, what is the frequency of the little d allele in this population? So in this case, let's walk through how we saw this. So first we got to write out what we know. So this disease is autosomal recessive, and only 1 in 150,000 are affected. So since it's recessive, that means the 1 is going to be little d. That one can't be any other genotype. So we know what this one is, and this one is going to be our q squared. So to find q squared, we take 1 and divide it by 150,000. Okay, so whatever the total is, you take the number of homozygous recessive and divide it by the total population. And that gives us, what was it? What did I get? Okay, it's a really, really tiny number. It's 6.67 times 10 to the -6th. It's a very tiny number because it's only 1 in 150,000 that are affected. So very low frequency. No, wait, no, is that right? No, that's the frequency of q squared. Yes, I'm sorry, my mistake. Yes, frequency of q squared. Yes. Then we take the square root of q squared, both sides. 6.67 times 10 to the -6. So we take the square root of both sides, and that gives us q equals, okay, 0.00258. Okay, so that's going to be the frequency of q, and that's the answer to part A. Now for part B, it's really easy because we just use this formula, P plus Q equals 1. We plug in our Q value and get P plus 0.00258 equals 1. And if we do some algebra, we get P equals 0.99. Okay, sorry, running out of room, sorry. 74. P equals 0.9974. Okay, now part D is, what is the frequency of the big D genotype in this population? So for big D, you take the frequency, this is the frequency of big D, so P equals frequency of big D. So to get 2 big D's in one individual, you have to square this. So that goes back to our P squared value. So you just simply take P and raise it to the second power, or in other words, multiply it by itself, and you get 0.9948. Yes. The next question is, what is the frequency of the big D, little d genotype in this population? So that is going to be our 2PQ, which is going to be, so that's going to be our 2 times our P value, which is 0.009974 times, run out of space here, times our Q value, which was, where was it?
Right there.
Right here.
Yeah.
Yes. 0.0022. Sorry, 258. So we multiply all that through, and it gives us 0.0052 is the answer to D. And then we can move on to question 2. That's that one.
Okay. So for question 2, it's our fill in the blank. So for 2A, the first blank is Q, second blank is 2PQ. For B, it is P to the P squared, or 2PQ. For C, we have Q squared. For D, we have R. For E, we have P squared, comma, 2PQ, comma, 2PR. For F, we have sickle cell anemia. For G, we have monomorism. H, we have subpopulations. And then I, we have major histocompatibility complex, or MHC.
Yeah.
So that is our fill in the blank. That'll take us to number 3.
I was supposed to do number 1. You were supposed to do number 3.
That's right. Well, do you want to do number 5?
Yeah, I'll do 5.
Okay, that's fine. Sorry about that little confusion there. So let's move on to number 3. Where's my? Oh, here it is. 1, 2, 3. Okay, so in this one, what is the frequency of the non-disease allele in the human population? Okay, so normally, yes, so normally we would take the number of whatever number they give us, which is in this case is 1, and divide it by the population. However, we don't do that this time because in this case, the 1 is going to be the diseased, and the diseased is caused by a dominant allele. So we do not do this for this question. Instead, we take 6,000 and subtract 1 from it, and that gives us 5,999. And then we take that, divide that by 6,000, and that's going to give us our, what does that give us? Number 3. Okay, 1 second. Yeah. Sorry, one moment. Yeah, that's going to give us our Q squared value. So let's move here. Okay. Okay. So that'll give us our Q squared value, which is 0.9998. Yes. So that is our Q squared value. So yeah, a lot of individuals who are homozygous recessive for this trait. Now, then the next one for part B, what is the frequency of the Marfan syndrome allele in the human population? So to get this one, the first thing we have to do is to take the square root of this to get Q. So we square root both sides. And that gives us Q equals 9, 9. It's 4 nines. 9, 9, 1. Right. Actually, it's could be 9, 9, 9, 2. Yeah. 1, 2, 3, 4. Yes, that's right. Okay. Sorry about that. So this will be our Q value. Now, to find B, you have to find the frequency of the Marfan syndrome allele. So this is the non-disease allele. So we just use our P plus Q equals 1 formula and find that, and do the same thing before, use algebra and find that P equals a very tiny number. It's 8.33 times 10 to the negative fifth. A very tiny number, which is why only 1 in 6,000 are affected. Yes. Now, part C is, what is the frequency of heterozygous individuals in the population? So to get that, we use our 2pq again. 2 times p times q, and that gives us how many is it? It's 3. 3. 6, 7. Yeah, gives us this for our frequency of heterozygous individuals in the population. Last question is for part D. Out of a population of 5 million people, how many heterozygotes are expected? So we just take 5 million, multiply by that number, and that gives us roughly 850. And so, yeah, that'll lead us to part 4.
Yeah.
Let's use this screen so you can see what you're doing.
So part 4 has a lot of calculations in it, so we're going to be using this board a lot. Oh gosh.
Sorry, I'm being tall.
That's okay.
Stretch.
Perfect. So to start off, we need to determine our allele frequencies. And to do that, we are so for the R2, we're going to take 2 times 135 plus the 44, and then take that divided by the 380, which will give us 0.8263, and that's for the R2. And for R3, we're going to do and take that over the 380, which will give us 0.1737. So these numbers are very important, and we're going to move on to B. So we're going to bring these numbers down and then square them. So for R2, it's going to be our R2 value. So the 0.8263, take that squared, and that'll give us 0.6827. And then for the R3, that's bringing this one down again. So the 1737, take that squared, and that'll give us 0.0302. 0302. And so to find our R2, R3, we need to do our 2 times 0.8263 and then 0.1. 871. And so from there, to find our expected values, we're going to take each one of these numbers times 190 to give us 1, 29.7266. 5.732. 54.5407. Perfect. And so we're going to take these and put them into the chi-square test. Very exciting. So we have 135 minus 129.7266. Take that number squared over 1 over expected value. So 129.7266. Those are sixes. And so we're going to do that again for each one. So we have 44.
Of course it would.
Oh, it's still going. Okay, good.
Okay,
It's back.
so then we're back. Awesome. That'll give us 7.0936 for our, I think that's backwards. Whoops. Our chi-squared. And because that number is so high, we're going to reject this. And we could, you know, say that we could reject this because it's not a very good sample, or there are many other reasons why this data set just didn't work. So that'll bring us to number 5.
Yay. Headphones.
Nice.
I can write this if you
Yeah.
Yeah, you've got some headphones. You listen to music while you listen. So you would listen to your video while you make a video.
Right? Can I pull up here?
Yeah.
Oh. Okay, oops. Okay. Suppose that a particular gene that controls coat color in dogs is controlled by 4 alleles in the population. These alleles are called chinchilla dog, white dog with dark eyes, pale gray dog, and albino dog. The alleles are given from the most dominant to the most recessive. Let's assume that a particular population of these dogs is in Hardy-Weinberg equilibrium. The allele frequencies for our 4 alleles are as such. So, for part A, what is the frequency of the chinchilla and the, what are you? And a pale dog. And then albino dog. So from those 3. So to do that, let's start off with the chinchilla 1. So you're gonna multiply all of these basically. So for our first one, we have 0.37 times 0.37 as well, or you could just square that, but who wants to? 1 over 1, because if you add all the frequencies together, it equals to 1. It should always equal 1. And that will give us 0.1369. So there's our frequency for the chinchilla 1. For our pale gray dog, we do, since it's like a heterozygous kind of form, we're kind of going to use the 2PQ-ish kind of thing. So we're going to do 2 times 0.25 times 0.15 all over 1 which is 0.075. There's our second frequency. And then our third one for our albino dog, very similar to the first one. We just do 0.15 times 0.15 all over 1, which will give us 0.0225. So here's A. Here's our A. Okay, B. So among the population of 2,000 dogs, how many would you expect to have the pale gray phenotype yet be heterozygous? So this is pretty much the same thing as the situation right here. We're going to use the 2PQ again. So we have 2 times the frequency for the CB gene, which is 0.25, and then you multiply that by the C gene, which is 0.15, and then that gives us a frequency of 0.075, and then we multiply that by the population, which is 2,000, which will give us 150. C, yeah, she can see all this. Cool. So for C, among a population of 5,000 dogs, how many would you expect to have the white coat with dark eyes phenotype yet be heterozygous? Again, pretty much the same thing. So we have our 2 times the frequency for the CD gene, which is 0.20. Oof, disgusting. 0.23 times 0.25. That's the frequency for the CB gene. Then we're going to add that to 2 times the second one, which is we're going to do 0.23 again. And then we're going to times it by 0.15, which is the frequency for the albino gene, which will give us 0.184. And then we multiply that by the population, which is 5,000, which would give us a total of 920. And then to finish this bad boy off with D, among the population of 15,000 dogs, how many would you expect to have the chinchilla, well, heterozygous chinchilla, or an albino genotype, whatever? So we would start off again with this situation. 2 times 0.37 for the CCH gene times 0.25 for the CB gene. Then we would add that to our albino gene, which is 0.15, and then we're going to square that because there's 2 of them, which will give us a frequency of 0.2075, and then we multiply that by the population of 15,000, which will give us 3,113. And that's all she wrote. Okay, bye.
Bye.
We're done. We just press stop podcast.
Yep.